guys. So in this next step, we have an isomerization reaction to turn everything into glyceraldehyde 3-phosphate. So that's how we transition from this left side of the screen to the right side. Before we go over this right side, the one thing you should appreciate is that everything on this left step is an investment phase, in that we invested ATP. So we have not harvested any type of energy-rich molecule yet. If you're curious why we decided to turn it into glyceraldehyde 3-phosphate instead of just using the DHAP, the reason is for this next step. So starting from glyceraldehyde 3-phosphate, which is this, exactly the same as this one. The next step is right here. And before we look at any of the enzymes or any of the products, let's look at the thing that changed. The only thing that changed is that we go from a aldehyde or a carbonyl to a carboxylic group. So this is an aldehyde group, this is a carboxylic group. And so in organic chemistry, I hope you guys remember that this is considered an oxidation step. So the first thing to note is that an oxidation step occurred. The next step that happened is that a phosphate attached. And then the next less obvious thing is that whenever you do an oxidation step, if you guys remember in organic chemistry, if there's an oxidation reaction, you must couple it with a reduction. And the reduction in this case is this part right here, or NAD positive, which I will introduce to you guys is an electron carrier. This NAD positive, which is an empty electron carrier, gets reduced to get NADH. And so to look at that mechanism in depth, I have it here. So clearing my drawings, we have this complicated mechanism, and I don't think necessarily important to memorize the steps, but what you should at least know is what are the most critical events of this pathway. So the first critical event is that somewhere along the mechanism, the NAD gets reduced. And so we see here, it uses a cysteine to attack the carbonyl. Once that carbonyl is attacked, we actually do the oxidation reduction first. So NAD pulls the electrons. So basically this H- bond gets taken by the NAD. And now NAD is reduced to an NADH. And because NAD got reduced, equivalently, the sugar became oxidized. And so now you go from this alcoholic group to a carbonyl group. And then when the phosphate can come in, then it can free the sugar from the enzyme. And one thing to note here is that this step does not use ATP. So this inorganic phosphate is actually just picked up from the environment. We don't use a kinase. So a kinase attaches a phosphate by using ATP or GTP. In this case, we actually just pick up a phosphate. So it might be a little strange to some people, but it just happens like this way. But the other most important thing is that NADH is produced. And we'll see later on, and you guys already know, NADH is used for energy as well. So this is like the first part of the mechanism where we harvest energy, and that the NADH is obtained. Okay. So we are now on this step. Hopefully I still have your attention. I know it's a very long pathway, but I hope I'm highlighting some kind of nuance on it. So now we generate this 1,3-BPG. So now we have 2 phosphates attached to our sugar, which should kind of hint us that we have 2 phosphates to harvest. And so the first reaction is that 1,3-BPG reacts with ADP. So basically 1,3-BPG gives the phosphate to ADP so that it becomes ATP. And this is often called substrate level phosphorylation because this phosphorylation reaction is done mostly by the substrate themselves without using any kind of electron transport chain. So same mechanism as Yaffe's metaphosphate intermediate that we've learned before, except instead of ATP giving the phosphate, it's ADP takes the phosphate from 1,3-BPG. And so if you're already seeing that this is a reaction where phosphates are transferred, you should not be surprised that the reaction enzyme name is a kinase. So this enzyme name for this step is called phosphoglycerate kinase. I know that it's kind of weird to see that ADP going to ATP is called a kinase because you might be thinking it's a phosphatase instead, but this is called a kinase anyways because phosphate is transferred. One thing to note I didn't talk about earlier is what do we call the enzyme name for this step? So this step is called a dehydrogenase. So a little preview, whenever an oxidation reduction reaction occurs, there's usually two kinds of enzymes that you hear, a so-called dehydrogenase and a so-called decarboxylase. And so usually when you release CO2 as a byproduct, usually and produce NADH, that's called a decarboxylase. But if you only kind of produce NADH as only NADH and don't release any kind of CO2, then usually it's called a dehydrogenase. So in here, this reduction reaction was done, oxidation reduction reaction was accomplished by a dehydrogenase, specifically the substrate dehydrogenase. Okay, almost done. So now we're at 3-phosphoglycerate, and we're going to 2-phosphoglycerate. So before I go over the mechanism, let's think about what the difference is. So the only difference is the phosphate is in the, if you guys remember your notation, this is considered the alpha carbon, this is considered the beta carbon. The phosphate is in the beta carbon, but in this next step, it's now in the alpha carbon. And so basically, they move the phosphate group to the next carbon on the molecule. And so whenever you have a reaction where something like one group, it could be a phosphate, it could be an OH, if one functional group is moved to the next, that is considered a mutase reaction. And so in this case, the enzyme for that is phosphoglycerate mutase. The mechanism in terms of arrow pushing is not super obvious. Let me clear my drawings. 1 second. So for phosphoglycerate mutase, the reaction is not as kind of straightforward. We actually don't show any kind of arrow pushing here. But what I want to highlight is that the way the enzyme works is there is a phosphate group available in the enzyme, and the enzyme has it in a histidine residue. So the first kind of novel idea here is that histidines can also bind to phosphates, not just serine, threonine, and tyrosine. The next thing is that the way it works is it attaches a phosphate to the right area first, so that now we have a doubly phosphorylated compound, and then it takes the incorrectly positioned phosphate away so that we recuperate the enzyme. And so just to kind of remind you, the way this enzyme works, it has a phosphate inherent to it. It attaches the correct phosphate first, and then it removes the incorrect phosphate. And so do you need to exactly know the electron pushing? I doubt that'll be a question, but if it is ever required, because this is a phosphate shifting mechanism, you can expect the whole pentavalent metaphosphate intermediate that we talked about with the Yaffe is the exact same mechanism that occurs here. Okay, we're almost done. And so now let's look at this step to this step. And if we look at this, the biggest difference that you should notice is that there was an OH here, and that there's no more OH here. It's replaced with a double bond. And so this is a dehydration reaction. And so in this case, even though it's a dehydration reaction, this was considered called an enolase. And the reason why it's called an enolase and not a dehydrogenase or something like that is that one, it's not an oxidation reduction step necessarily because we don't produce any NADH. But second, the final product, this is a double bond next to an OH. Ideally, you'd think this is an OH. So this is considered an enol. And so that's why the enzyme is called enolase. This last step is the most crucial because we're finally at our final product in glycolysis, which is pyruvate. The first thing you should notice is that ATP is produced. So if you're already thinking what enzyme does this, you should already think it is a kinase. And so, great, the enzyme name is pyruvate kinase. The other thing to note is that our kind of like, the way I'm teaching this is that we like to notice the differences.